Hello everyone, welcome to this material characterization online course organized by NPTEL. We have been seeing in last few classes the tutorial sessions of optical and other characterization techniques. In today's class, I would like to start a tutorial session on a scanning electron microscopy. I hope you all have gone through the theoretical lectures of this scanning electron microscopy, where we have discussed in detail the principles of scanning electron microscopy, the physics behind it and theory, and also the instrumental details and image formation mechanisms and so on. So, in order to just recollect and realize how it is done in a typical laboratory experiment, we have also demonstrated how to grab the image in a scanning electron microscopy. In this class, what I will do is I will present a couple of case studies where we will just show some of the images taken from SEM and then try to understand how to interpret this and some of the do's and don'ts of things which you when you perform scanning electron microscopy. So, as we discussed in the theoretical classes also, you have to be very clear before you start your experiments. You have to clearly define your objectives, what exactly you want from this microscopy session. So, that is primarily an important factor, and for example, if you just want, whether you want to just look at the surface topography, or you would like to examine the fracture surface, what kind of fracture surface, or you are interested in looking at the second phase distribution and so on. For example, even if you are interested in looking at the porosity level or the coating thickness or a cross sectional study. So, the objectives have to be first fixed clearly before you really perform the experiments. Then you can, without wasting the time, you can just go to the microscope and then look at what you really want without wasting much of the time. Okay. But before that, we should also know how to prepare the samples. For example, I have just demonstrated in this course various types of sample preparation techniques, and depending upon whether it is an optical microscopy or a scanning electron microscopy or even a transmission electron microscopy, XRD and so on. So, and it also varies with specimen to specimen or sample to sample or material to material. The sample preparation technique also vary as you have clearly evidenced in the video demonstrations. So, today what I will do is I will just present So, what I am going to present today is two case studies. The first one is a polycrystalline alumina, and then the second one is a thin film of aluminum deposited by chemical vapor deposition on a titanium nitride, titanium and silicon dioxide coated silicon substrate. So, you have the silicon substrate and over which you have the coating of this and over which you are depositing the aluminum. So, how to examine these kind of materials in an SEM, typical SEM. Okay. So, the first point is sample preparation, how to prepare the sample. First we will take the case study 1, we will take the polycrystalline alumina. So, what are the steps for the sample preparation? And then objectives. So, first we will say objectives. What are the objectives? In this case, the objective is so, like I mentioned in the case study, you have to be clear about what are the objectives. In this case study, we are interested in checking the residual porosity and determine the grain size and establish that grain boundaries are free from second phases. So, let us see how we will examine these things in this case study. And SEM is the one of the best technique to look at the residual porosity in a material. And now look at the sample preparation steps, how to prepare the sample. So, we can prepare the samples by two methods. Either you follow step 1 where you do the mechanical polishing down to a sub micrometer diamond grid polish, followed by thermal etching to form grain boundary grooves. So, normally any etching activity will produce a grain boundary grooves on a polishing surface. So, in this case you do a thermal etching and then you have the polished surface ready for the examination, or the second way of doing this thing is either you break the some suitable mechanical specimen so that we can examine the fracture surface. So, there also you can find out the kind of features we are interested. So, that is another way of doing this. So, remember alumina is an insulator. So, we need to take care of the conductivity of, see if you recall the lectures, to examine the electron under the electron microscopy, the material should be conductive. So, we need to make the surface suitably conductive enough before we try to examine the samples. So, what will we do? So, we can use any of the conducting coating on the specimen surface before the SEM analysis is taken up. So, these are the important steps you have to consider before we go to the SEM analysis. So, I will repeat quickly. We are now looking at the polycrystalline alumina under SEM. So, the first step is the things which you have to keep in mind is you should have clear objectives and you should know how to prepare the sample suitably for the examination. So, in this case the objectives are examine the residual porosity, determine the grain size, establish the grain boundaries are free from second phases, and you can prepare the sample in both ways to look at these objectives. The first one is very conventional and standard one, mechanically polish down to a sub-micrometer diamond grid polish followed by thermal etching to form a grain boundary grooves, or you can break a suitable mechanical specimen so that you can also analyze the fracture surface. From there also you can get these kind of information. You can examine these objectives on the fracture surface as well as on a polished surface. And when you come to polishing, alumina is an electrical insulator. So, we need to coat the surface with some suitable conducting layer, whichever is available in your laboratory we can use, either a gold coating or a carbon coating, etc. Normally people use a coating unit. So, the next thing is what I will do is I will just go to the slide and I want you to look at this image. There are two images A and B. They are all SEM micrographs of thermally etched polycrystalline alumina recorded using 5 kV electrons to minimize the charging, and then 20 kV electrons. You have you can see the difference in the image quality. So, here in this image there is no conductive coating was present on the specimen. So, you can see that charging is taking place. So, what is that you make out of this two micrographs? One is taken at low kV and one is taken at higher kV. You can see that higher kV does not help much in getting the good images. So, all that you have to remember, you have to go back and recollect what all we have discussed in the theory classes. I just mentioned in the image formation mechanisms, in SEM you form an image primarily by the secondary electron which is coming from the surface, immediate surface. I also mentioned that you have SE1, SE2 and SE3. For example, the secondary electron which comes immediately from the surface, primarily they are all SE1, secondary electron one category, but then there are some secondary electron which will escape from the subsurface from the detector they are all called a secondary, a secondary electron 2, and then there are some stray electrons will hit the column, they are all categorized as Se3. So, the interaction of these Se electrons also will have a significant influence on the image quality. Remember, if you recall the instrumentation video, the secondary electron detector is kept on the side of the electron column. In fact, backscattered detector is just fitted on the pole piece just above this sample, but your secondary electron detector is always kept on this side. So, the collection efficiency is always can be shadowed from some of the detector positions, and that is why these days you also have in column lens or in lens detector or annular detector which can effectively collect all the secondary electrons to form an image. So, but then here what we are now looking at here is why I am bringing this detector system, because when you have the in lens detector which can collect the secondary electron effectively, and the reason for in this particular image what you are seeing as charging is, we have also discussed in the theory class the effect why the charging occurs, because most of the secondary electron which is emanating from the surface are hindered, or they are not collected properly, or they are interacting more like with Se2 and Se3 and so on. So, higher voltage does not improve the image quality, because it also hinders the secondary electron which is coming from the surface quite a bit. So, the lower kV is the better way of using this. So, we will write it down some of these observations so that you will not forget these things. Why we are getting charging effect? Because so, why you produce a bad image when you use a higher kV in this case? When you use a higher accelerating voltage, that leads to unstable surface charging of the specimen. So, which affects both First is secondary electron emission coefficient, that means the secondary electron which is coming from the surface itself is affected, getting affected, and then the trajectories of the secondary electron being collected. That is why I just said that if you recall or look at the video again, the secondary electron detector is kept in the side to the with respect to the specimen. So, the secondary electron trajectories itself is getting affected by this charging. So, you get a very poor quality image. So, how the lower kV is able to produce good image? Because you will write low kV effect, you write So, when you use a lower kV, in this particular case 5 kV, the incident current is compensated by the exciting the secondary and backscattered electron. So, charging is reduced. So, you have to remember, so whatever the incident current which is falling on the surface has to be nicely compensated by the emission of secondary and backscattered electron. So, net charging is reduced. So, that is the point. So, if you have the higher kV, then this is not happening. The more and more an electron will go and bombard on the surface, which will promote the charging effect, which indirectly will hamper the image quality. So, that is what you have to realize, effect of using higher and lower kV on the image quality. So, this is a secondary electron image what you are seeing, and then you can also now see that then SEM micrograph clearly showing the fine surface facets on a thermally etched alumina. The image was recorded using a field emission gun and a specialized secondary electron detector. So, most of the contrast comes from Se1 electron. So, you can look at the micron bar, this is about 200 nanometers, you are able to resolve this nicely. So, if you want to write something on this specimen, you can write. So, So, what I have written here is nothing but what we have already discussed in the theory classes. You have the SE1 which is generated from the near surface region by the primary beam, which is primarily responsible for obtaining a surface topography. You can just go through the lecture again. And then you have some SE2 which are coming from the subsurface, then again escape from the detector, and this is primarily observed when the voltage is more than few hundred volts. And there is something called SE3, they are stray electrons striking the chamber or column or a specimen holder, which again deviates from the trajectories. So, these things will contribute to the image quality. So, the one which you are seeing on the slide is the is recorded at the field emission using field emission gun, primarily by the SE1 electron contrast. So, very fine contrast. Then we will see that the same thing, same specimen, but it is a fracture surface. What you are now seeing is fracture surface of alumina showing a cleavage facets and the intergranular failure. The images were recorded using both a conventional secondary electron detector, that is A, and the in-lens secondary electron detector B. More detailed features of the fracture surface are visible in the image from the in-lens detector. So, what I have now tried to say by this images, see, look at this images, let us understand what is this a conventional ET detector captures. You can see that facets all fracture surface, and you have the intergranular fracture you are able to see, but the contrast is better here when you have the in-lens detector. So, what I just mentioned a few minutes back, if you have the in-lens detector, it could be an annular type. What it does is all the secondary electron which is coming from the surface, immediate surface, are effectively collected, rather than by a secondary electron detector in a conventional ET detector which is kept on the side to the specimen. So, the electron trajectories have little deviated, it has to be really tilted, and the specimen has to be tilt should be effective enough, so that all the electron trajectory is moving towards the ET detector. But if you have an in-lens detector, you do not have that problem, it will effectively try to collect as much of the secondary electron emission from the immediate surface. So, the collection is very effective, then the contrast is much better. That is what you are evidencing here. If you have the in-lens detector, you have the better feature, the better contrast you are getting, or you are also seeing the much more details. You can see that the details which is there in the left corner side is much more better when you have the in-lens detector. That is because the detection capability is high, and also remember these are all again secondary electron image, and this is how it is interpreted. So, you should have some idea about why this two different contrast is obtained on a same specimen and same fracture surface, but you are able to detect these features which we are interested. So, for example, the objectives what we have just narrated about the intergranular and fracture surface, and we wanted to understand the grain boundary, whether it is free of second phases or not, and you can clearly see such analysis. So, we will quickly go to the next one, is basically looking at the fracture surface much more closely. The same, a secondary electron micrograph is shown here. This again thermally etched alumina. The fracture surface of the alumina is shown on the right hand side, showing the transgranular fracture, this cleavage. So, all these facets, they are all a result of a cleavage, transgranular fracture. And then you have the grain boundary fracture, you can see here, these are all intergranular fracture, and you can also see the pores here, you can see nicely the pores both on the grain boundary as well as within the grains. So, see, one of the primary objective of this case study was looking at the grain size, which is typically the facet size, as well as looking at the grain boundary, whether it is free of second phase particle, and also examine the residual porosity like this. So, we can clearly identify all of them. Let us see whether we can write something about these features. Okay, this is nothing but a secondary electron image, and all that I have just described is we have already written in the objective, so we do not have to write it again. You have the pores and facets and intergranular fracture. So, now we will move on to the case study 2, that is, so this is about a thin film of aluminum deposited by CVD on a Ti and Ti SiO2 coated silicon substrate. So, objectives we will write. So, here in the second case study, what are the objectives? Initial deposition conditions where the first aluminum nuclei form on the surface of the TiN, titanium nitride, and the morphology of the final aluminum film, the morphologies of the underlying titanium nitride and titanium films. So, you have titanium nitride and titanium film. So, these are the broad objectives of this case study. So, sample preparation, if you look at the sample preparation, since it is a metallic sample, you do not have to worry, which is a conductor. So, directly it is very straightforward, and then and looking at the the first objective is looking at the initial conditions of aluminum nuclei is which is very small. Since it is very small, we have to keep that in mind, that we may require a very high resolution and a low kV in order to avoid the charging as well as the contamination. So, since we are interested in looking at the earlier nucleation of aluminum during after the deposition, the surface contamination can be a very critical factor which will limit the contrast and resolution. So, you might ask that what about the previous case, there also it is high voltage will produce there is a possibility of producing contamination, but nevertheless the objective here is to looking at the very surface coating which is very thin, and also the aluminum nuclei is very small. So, the contamination could be the major critical factor in this case rather than the earlier case. So, you have to look at this point very clearly. So, what you are now seeing on the slide is a very interesting slide. You can see that the secondary electron image again it is taken with the in lens detector. You can see that aluminum particles are very small, the coating initial nuclei on the titanium nitride recorded with 1 kV incident electron beam. Remember, it is taken with 1 kV. The initial beam was focused on a central region here of the micrograph for approximately about 30 seconds, and then magnification was reduced and the micrograph was recorded immediately. The buildup of contamination in the central region strongly affects the contrast and resolution of the image. So, what you are seeing is a black region. It is because of the exposure, overexposure of this electron beam, and remember here it is 1 kV is being used for 30 seconds. In spite of that, the contamination is so fast, but then you have to reduce the magnification because you are interested in looking at the aluminum nuclear particle. So, the image is taken immediately. So, this is one typical case study which clearly demonstrates how the contamination can affect your resolution and contrast in SEM. So, similar precautions you should take when you really want to examine such samples. So, this is another interesting study. So, we can also now focus on the other two objectives, looking at the morphology of final aluminum film and morphology of underlying titanium nitride and titanium films. Probably I will take it up in the next class. Thank you for your attention.